Thank you for this wonderful idea, Dave, of having this this going on. Okay. Let's see. So that's. Oh, this is an upside-down house in Moscow, and this is when you get inside of it. Everything is upside down, and this is the title of the talk. I'm very happy. Let me make the point that this really is a joint work with Lenore and Avram. And Lenore and I, we work the way people work in cryptography. One person comes up with the algorithms, the other breaks them. So Lenore and I work together. I work trying to understand pain, the feeling of pain, and Lenore couldn't understand why, and she's working on trying to understand the feeling of joy. You can see how we separate things. And the one theorem that comes up, that's due to Avram. So let me start first by saying something about, a little bit about how, it's very nice that Dave said I've been working on this for 75 years, because it's true that I'm 80 years old now. And when I was about 5 years old, I was a very dumb kid. Really, it was terrible. I wanted to be smart, but I just couldn't hold things in my memory. I just couldn't. I didn't realize at the time that if you don't speak the same language as they speak in the school, then that makes things a little hard. But nevertheless, I really wanted to understand how to think, at least memorize. So I asked my father, "How do you memorize?" And he said, "You just do." Well, this didn't help me, so I asked again, and I pestered him, and at some point then he finally said to me, if you understood how the brain works, you could be smart. And I thought, that's a great idea. And that was, hey Shafi, that was what motivated me after that. And I can remember thinking when I was in fourth or fifth, we kept on moving, so I can say it was fourth or fifth grade that I was thinking about wanting to understand the brain and trying to get a sense of what's going on inside. And the sense I got was that there's a homunculus. I didn't know it was called that, but it was like a little person in my head that was seeing outside of my eyes and making decisions, and all I had to do was understand the brain of the homunculus. And I realized at the time that this was not going to work. That was a problem. Let me just mention also that later when I was, I apprenticed, as a junior in college, I apprenticed myself to the famous McCulloch Pitts. McCulloch Pitts were my real mentors. They're very important because McCulloch Pitts defined the formal neuron. It comes from them. And they had many consequences from this formal neuron. They were able to prove that with this formal neuron, you can build a circuit that can, given some paper, simulate a Turing machine. Nowadays we know that, but at that time that was interesting and new. That was 1942. And yeah, so I apprenticed myself as a junior. So I worked in a neurophysiology lab for a number of years. One of the things that came out of this paper was that McCulloch said, these circuits cannot work unless they have both inhibition and excitation. And the neurophysiologists of the time said, well, we've seen excitation, but there's no inhibition in the brain. And in fact, they only found that inhibition after he pointed it out and said, it's got to be there. Because without inhibition, as you know, when you get more excitation, more things fire. You need to have it. He proved it. So I thought that's a wonderful example. Right. And then I went into recursive function theory and logic because I was hoping that that would be the mathematics that would help me to understand the brain. I wouldn't recommend that now as the mathematics to understand the brain, but that was then. Okay, so here's the, let me start with this, oops, let me start with what is consciousness. So I need to tell you, we have to agree on the terms here. So roughly speaking, consciousness is what you are aware of. Hi, Fritz. Consciousness is what you are aware of. It's, you know, it's what you see, what you hear, what you feel. That's what you are consciously aware of. It's also your inner speech. You are conscious of your inner speech. You all talk to yourselves all the time. It may be, Yael probably talks in Hebrew, but I talk in English, you know, and I'm quite sure my dog is conscious and talks in doggish. But we all talk to ourselves, and this speech is important because that's how we do planning. Your dreams are something you are conscious of, but dreamless sleep, you're not conscious. You are conscious of your dreams. You may forget them, but while you're dreaming, you are conscious of them. And your feelings. Okay, let's keep on going. Some examples of what you are conscious of and what you're not. So, you know, have you had this experience? You go to a party, you see somebody you know, but you can't quite get their name. And it's very embarrassing, and it's hard, and so you go and get yourself a glass of wine, and you talk to somebody else, and then maybe you've had the experience that half an hour later the name pops into your head. What's going on here? Well, you know, you've been talking to somebody else. You haven't been thinking about it. It's coming from your unconscious. It's down there deep. There's a part of your brain that's been working on this problem. What's the name of that person? And that half hour later, it comes up. There are other examples. So problem clarification and incubation, I'll talk about that. You know, that I've spoken to ping pong players, good ping pong players, and they tell me that when you're learning to play ping pong, you pay attention. But when you're in a tournament, you stop. You take your consciousness out of it, and you let your unconscious brain do all the work. That's the sense of these expert ping pong players. Problem clarification and incubation is going to come up because what's come out of the model I'm going to be presenting is that really you consciously can specify and clarify the problem. You can look at it from many different angles, but the answer to that problem is not coming from your conscious self, it's coming from your unconscious. So there's this clarification, which is what you do consciously, and then the incubation, the actual getting to the answer, that's unconscious. And so examples of this, I have several from Hadamard, Poincaré, Gauss. I have to add one. Umesh was telling me that there's a wonderful one from Ramanujan of this sort. Hadamard saying, on being very abruptly awakened by an external noise, a solution long searched for appeared to me at once without the slightest instance of reflection on my part. Just from nowhere. Poincaré, this is one that the mathematicians know about, saying, as he was about to board a bus, the idea came to me without anything in my former thoughts seeming to have paved the way for it. And then he says what came to him, the important thing. And the point again being, you clarify the problem and then your subconscious will solve it for you. And you know, Gauss, our first theoretical computer scientist, saying, after years of failing to prove a particular mathematical theorem, I finally succeeded by the grace of God, like a sudden flash of lightning. I myself cannot say what was the conducting thread, which connected what I previously knew with what made my success possible. So this again, this difference between what's conscious and what's unconscious. So what is consciousness? So this talk is going to present a formal model of a Turing machine. Not everybody calls it, some people don't think it's a Turing machine, but I just mean by Turing machine, it doesn't look like a Turing machine at all, but I mean by this something that's formally well defined. and maybe I should call it a conscious AI, depending on what we want to emphasize. And so I'm going to show you the formalization. And after formalizing it, we're going to define consciousness in that model. So I would just want to make the point that when I say consciousness, I'm meaning consciousness in that model. It's not necessarily the consciousness that you feel is in your brain or that you are conscious of. I'm going to define it, and that's consciousness in that model. And if I say consciousness, you can remember that I'm referring to that. And how good the formalization is, well, the quality of a formalization and definition depends largely on how closely the notion squares with what you think it should be, and whether or not it helps you to understand the concept, and you will be the judge of whether it's a reasonable model or not, reasonable definition or not. Okay, these are lots of different wonderful cognitive psychologists and neuroscientists. Bernie Bars is the one that came up with the initial model that I'll be telling you about. Stan Dehaney is very important, and thanks to Fritz, I learned about Kevin O'Regan's work, which is absolutely wonderful. Bjorn Merker, right after him, is important because he's the one that says you don't even have to have a cortex in order to be conscious. Whether that's true, I'm not sure, but there's evidence that you don't need very much to have consciousness. And at some point I can tell you about some of the interesting stuff coming out of that. Okay, so let me get to the problem that interests me the most here. And David Chalmers is a philosopher who defines the hard problem, the easy problem and the hard problem. And he says the easy problem is to make a machine that simulates feelings, and the hard problem is to make a machine that really feels. And as engineers, we know how to make machines that do things. But if you can find on YouTube a machine that is very afraid of a red ball, and you see when it sees this red ball, it puts up its hands, it cries out, it tries to stay away, but you know that that's a simulation, that's not. So the question is, what is it that really generates the true feeling? And for me, it's hard enough just to try to get to the basis of the feeling of pain. And I think I do have it. You will not agree, but I do think I understand where the pain is coming from. And Lenore is working, as I said, on joy. Let me say that Chalmers' definition is a lot more general. He's interested in all qualia. But our research and this talk is restricted to understanding pain and joy. That's it, including the extremes of agony and ecstasy. So the easy and hard problems. Our research in this talk, I said, and we have a reasonably good answer for pain, but only a partial answer for joy. So what can theoretical computer science contribute to this discussion of consciousness? First of all, we are looking for simplicity, not complexity. When I talk to John Anderson, he says, the brain is very complicated. You're trying to get a simple model, forget it. The brain is very complicated. And yes, I understand that, but we are looking for a very simple model so that we can understand it and maybe be able to prove theorems and simulate and do stuff like that. So he doesn't think we can do that, and, but I know that he says evolution, this quote, evolution abhors parsimony, and we say mathematics thrives on it. And our aim is to propose a very simple model that we can understand and prove theorems about. We want properties of consciousness to be emergent, not programmed in. We'll have a feeling that it really does have we'll believe more that it really feels the pain when it does something to prevent pain, because that wasn't programmed in, that it really wants to stay away from pain. So let me explain to you the difference between simulation and experience. They're quite different. And I especially like working with pain because the difference is so startling there. And I'm going to talk to you about the disorder called pain asymbolia. You can look it up, but if you look up asymbolia, it's the wrong word. It's pain asymbolia. It has other meanings. Pain asymbolia. And there are two kinds, pain asymbolia 1 and pain asymbolia 2. Okay, I have to talk about it. What is this pain asymbolia? Pain asymbolia, a kid that has pain asymbolia knows about pain. You can prick them and pinch them in different parts of the body. You can make it hot, you can make it cold. It knows everything you know about that. It knows about the pain, but it doesn't bother it. The young girl, the 7-year-old girl who has pain asymbolia, when you do this, she giggles because she knows how strange this is to the rest of the world, that she knows about it, but it doesn't bother her. Wouldn't you like to have that sometimes? No, you wouldn't. So kids that are born with pain asymbolia rarely live past the age of 3. And this is very important because we might ask, well, why do you need to have the feeling of pain? And here are kids who know about pain and, okay, good. So, so pain asymbolia. There are two kinds of pain asymbolia. One where the kid doesn't show any pain at all, pain asymbolia 1, and there's pain asymbolia 2 where you see grimacing and all the signs of pain, but even though it's showing the signs of pain, the person doesn't really feel pain. You know, one of the experiments I like to do when I was thinking about this is I would take a very cold can of Coke out of the freezer. You take one that's partly liquid and partly frozen, and you try to hold it in your hand for as long as you can. And I can hold it for some seconds, 20 seconds, half a minute. It's very hard to do, and then I let go. You give a can of Coke like that to a pain asymbolic person, and they can hold it forever. They know it's frozen, they know that, but it doesn't bother them. Okay? So consciousness has to do with the architecture of the brain. And the architecture, so let me say that the architecture presented here deals with the brain at a very high level of abstraction, a level way above that of neurons. I did work in the neurophysiology lab. I know about neurons, but I don't know that much. And I'm at the level of trying to get the simple model, and it's well above the level of neurons. So you won't see neurons in this talk. What you will see is this architecture, which is absolutely not obvious. It's called the theater model, or global workspace model of consciousness. So, you know, I mentioned to you that as a kid, I tried to understand what's in that head, and the best I could get is just like a homunculus in there, which I knew was not bad. And I was so happy when I learned about finite automata, because I thought, oh, wow, that's a model of the brain. That's going to be my model of the brain. And, but, you know, I soon enough realized, well, what was nice is that was when I was a sophomore and learning about Plato. And Plato talks, basically his model of the brain is a finite automata. He says, when you're born, you start off in the start state, and you find your way to the state which corresponds to the language that the people around you are speaking. He specifically says you are born with the knowledge of all the languages in the world and all the languages that there could be. Your problem is to reach that state where you know the language. So of course that didn't work very well, but I knew that didn't make too much sense to me. And then I learned about Turing machines. Oh, wow. That's much better model, but there are reasons why even that's a problem. I wanted to have a good model, and the first one I learned about was from Bernie Bars. So this I consider to be a wonderful model. It's Bars' theater of consciousness. So he talks about us, our consciousness, as being the activity of actors in a play performing on the stage of working memory, working or short-term memory, the performance observed by a huge audience of processors in long-term memory. So I will talk about just two memories, short-term memory, long-term memory. Those are the only ones that will come up here. I've had people, psychologists, come up afterwards and say, you know, there are many memories. What is this? You just have two memories. And I was very happy when this psychologist, graduate student, told her he's just trying to get a simple model. So that was very, very nice. So you understand this? There's an actor on the stage. That is what you are conscious of. That's it, just what's on the stage. The first person to actually come up with this was Hippolyte that I've been able to find, and he said there's one at most two. And now, then there was a while, there was George Miller came up with this notion that you can actually have in your working memory up to 7 plus or minus 2 chunks. Have you heard of his paper, the magic number, 7 plus or minus 2? It's the reason that you can remember a 9-digit phone number long enough to find a piece of paper and write it down. But if it's 10 digits, 10 random digits, of course it starts with 1, it's really 9, but if it's 10 random digits, you will find it very hard to find that paper and write it down. 7 plus or minus 2 chunks is what George Miller said can be up there. And of course these processors, the audience, is many different processors, each concerned with their own specific interest. One of them is especially concerned with faces. It recognizes faces. It's sort of like the camera that, you know, puts a box around all the faces it sees. So there's a fusiform face area that's concerned with faces, and it shouts when it sees a face. So there's more than one member there that's concerned with faces. Okay, so here's another point. The conscious self is not privy to the workings of the unconscious self. So you don't really know how that unconscious self is working. You know, you would like to know? No, sorry, you can't know. I mentioned to you, you know, you see somebody and you don't remember their name. That's what's happening here. What's her name? Okay. So the conscious self is not privy to the workings. You recall, in this case, you recall when you first met, perhaps. So I'm now talking about this theater model. You consciously, up on the stage, recall, you are asking the question, what's her name? You want to know what's her name. And then up from the bottom, that's the red, you recall where you first met. And that might come into consciousness. Oh, good. And it gets broadcast. What's on the stage is broadcast everywhere. And then some other processor, making perhaps use of that fact, says something about what she does. And that helps, and it gets broadcast, and maybe then her name begins with T, and that gets broadcast, and finally that half hour later comes from the audience, from the unconscious, the name of that person. The conscious self on the stage does not know how or where her name was found. That's very interesting. I sort of, if I want to make a model of this thing that might be useful, it's sort of like having an iPhone, and when you want to find the name of somebody, you're not sure, should you look it up in the address book? Maybe you have her name there, maybe not. Do you look it up in your calendar? Where do you find it? You might look up, you might go to Google, lots of different places. So wouldn't it be nice if all of those processors, those apps, did the looking for you, each one looking for what you want, and finally when one gets it, up it comes. So that would be, I would like an iPhone built that way. Okay, here's Barr's model. Now this is his particular model of consciousness. You see coming in on the left, vision, hearing, touch. His conscious event, the working memory. You see up on top the central executive It's sort of like a Turing machine has a central executive. We're not going to have that in our model, no central executive. And then the response out there. And down below, this is just a sample of the various different memories and processors that are doing the work. Okay, so what can theoretical computer science contribute to the discussion? So a well-defined formal model. That's what I want. Very well-defined formal model. A good formal definition of consciousness. So I will give you a definition of consciousness in the model. Explanations how agony and ecstasy might arise in a machine. You will not be happy. Well, let me say something about this. When I talk to people, there are some people, when I tell them I want to come up with where the feelings come from, who say, you cannot explain that. It's just out of reach. Science cannot explain that. And I probably can't change their minds. I try to change their mind by saying, you know, at one time, science could not explain life from non-life. They seem so different. What's the spirit that makes for life? And yet, you know, F equals ma works for that. And I think the same thing is true here. We have the sense that maybe you can't explain agony and ecstasy. I think you can, and I am trying to do that. And I think I at least have some explanation for pain, which you probably won't agree with, but I have ways to check whether it's any good. Understanding, I want understanding for distinguishing simulation from experience. And this has a practical application. You know that if you go to see a doctor, they don't have a very good way to tell how much pain you have. And my shoulder is hurting. And the doctor shows you some photos, a very happy person, a crying person. Well, where's your pain? And asking the person, and the doctor doesn't know, is this person really feeling the pain? Or does he just want the pills so he can sell them on the street? So one of the applications of this I'm hoping for is a way to tell, a way for the doctor to distinguish. The important thing about that's possible application, but the important thing for this talk is that without understanding, there's no way to tell if an entity, an animal or robot, is conscious. There's just no way. You know I'm conscious because you're conscious, and you know I'm built more or less the way you are. So that's how you know that I'm conscious. But how about a dog? Is a dog conscious? How about a fish? Is a fish conscious? How about an ant? Is an ant conscious? Where does it? Without understanding, you simply have no way to tell. I mentioned the fish and the ant because the mirror test that psychologists have for talking about self-awareness actually suggests that an ant, the Myrmica ant, actually is self-aware. And the mirror test also says that a fish, not all fish, but a particular one called the cleaner wrasse, is actually aware of itself. It's interesting, you know, you dab a little paint on the forehead, and then when at some point they see a mirror, they see itself. So this ant and this fish both recognize themselves in the mirror. Fighting fish, when they see themselves in the mirror, they try to fight. But this cleaner wrasse actually doesn't try. It sees itself, it sees that there's some paint on it, and it tries to rub it off. It doesn't try to rub off the paint from the fish in the mirror. It tries to rub off its own paint. If it sees this paint on another fish, it does not try to rub it off that fish. It's trying to rub it off itself. You see, this mirror test is a beautiful test of awareness. It's not the best test because gorillas don't pass the mirror test. You know why? Because it is taboo for a gorilla to look another gorilla in the eye. That's bad. You look another gorilla in the eye, you can get killed for doing that. So of course they don't pass the mirror test. Anyway. Let me make a point here that the purpose of the conscious Turing machine is not to compute uncomputable functions. That is not possible. Okay? Nor is its purpose to compute functions more efficiently. That's not the goal here. This conscious Turing machine does not compute anything else, does not compute anything necessarily faster. Its purpose is to suggest possible solutions to the hard problem. That's the whole purpose. And so, see, that's a different problem from the ones that most of you are working on. So you can leave now, because this is different. Anyway, okay, so here's the conscious Turing machine definition. So you understand what I'm trying to do? I'm going to give you definition of what I call this conscious AI. Okay, so as with Bernie bars, you see there's an input, and then there's this short-term memory, which represents the stage, and then there's the output. And then there are all these processors down below, which are doing the heavy lifting. And whatever's on the stage gets sent down, is broadcast to all the processors down below. There are reasons, so Koch thinks that this model is not very good because it's just binary branching. Whereas he says he's found neurons in the rat brain which just wrap around the brain and send fibers everywhere. So that it's not just binary, it's much higher. But this is a model, and I want to keep it simple. And so it's binary in the model. And the binary is nice because you know that with very narrow depths you can get to a lot of processors. And so this is doing just that. Everything comes down very quickly. Whatever's on the stage, every processor knows about it as input. And no central executive. Each processors can take the place of the processor up on the stage. Now they don't actually move there, and that's, but we can explain that later. This green arrow represents information being broadcast, and then information goes back up to the stage. These are the green and the red are very different. Oh, by the way, let me just say that two different trees, but this is too complicated for me, so I'll just show you one tree, okay? But there really are two trees, one for coming down, one for going up. Coming down, very easy for information to get to the long term because information just splits. It comes down to a node, splits. Comes down to a node, splits. So that can be done very quickly. Going up, that's a little bit harder because, you know, these different processors have different kinds of information that they want to send up to the stage, and the stage can't hold very much. It's just 7 plus or minus 2 chunks, as they call it. And the question is, what will actually go up? So initially, our model had all sorts of two nodes here, having to decide which one will go up. And that was too complicated. And so the model became simpler when we finally decided these processors, they have a number which they assign the process. Whatever it is, whatever that process is, each one assigns a number, and that weight is what will help it decide whether it gets up or not. So some of the weights start, for example, the pain. You know, I'm interested in pain, so what's the weight? There's a processor there that knows about your big toe. And if that big toe is sending a signal to your brain that there's pain, then you have a weight which is determined by how many nociceptor fibers are firing and what's the frequency of the firing. So that pain processor can assign a weight. And each of these processors does have a way to assign a weight. And in many cases, the weight is determined by how many neurons are firing. Joy, well, it's probably many neurons firing, and it's the number of neurons firing and the frequency that decides the weight that the processor gives it. Each processor is basically trying to assign some sense of how important its information is. So here's the information going down, and here's the information going back up. And you can see here, I've got pain with -5 and joy +3, And the decision is a very simple one. They simply add the two numbers. -5 plus 3 is -2. And which has the bigger magnitude? Pain has a bigger magnitude than joy. Pain goes up with a -2. And then here's pain -2 and fear -5. The one that's the bigger magnitude, bigger weight is fear. It goes up with the sum of the weights. I love this because initially the model was much more complicated with its communication. What I especially like is that around this point I discovered that Abrams has this model of information like this where he has a theorem. I told you one theorem. He has a theorem about how these weights should be dealt with. You know, one processor may think its information is very important, and another one thinks its information is not very important. And you have somehow this must be dealt with. You have to have some way of saying this processor thinks its weight is too important. We've got to reduce it. This other one thinks isn't happy. We've got to increase it. So we've got to. So there is in the background here an algorithm which Avram proved is an optimal algorithm for adjusting those weights. So the processors themselves determine the weights, and his algorithm adjusts them so in an optimal fashion for getting up there. Oh yeah, so good. Okay, so this is see fear changing. Things are changing constantly. Okay, the point of this. You like this frying pan? Found a nice frying pan there, and the purpose of this is that there's stuff bubbling down below, and these adjustments are constantly being made. Each processor has some information that it wants to send up, and sometimes the information is more important, sometimes less important, and these are changing all the time. And finally, some processor's information gets up to the top with its corresponding weight. There are theorems one can prove, that some very simple theorems, like for example, this way of deciding how summing weights tells you that when you get to the top node, whatever it is, if it's negative, this is an unhappy world. If it's positive, that's good. There are these positive things, there are these negative things, and just it turns out that the sign of this, whatever it is that's on top, is actually the sum of the signs of everything below. It doesn't mean that the particular thing on top is the most important thing, but it does tell you whether it's a happy or unhappy event. The reason, just going back a second, what's going on here is I wanted to make a point about a particular example of this sort of thing. Have you read Oliver Sacks? Some of Oliver Sacks' wonderful writing and very interesting. He talks about wonderfully interesting things, well worth reading. And too bad he died. But anyway, one of his stories is about being in the Swiss Alps, and being in the Swiss Alps, he likes to hike, and being very high up, and he comes to a fence and he sees a sign. And the sign says, "Beware the bull." So he looks left and he looks right, no bull. So he goes in, and he talks about going in, and he's enjoying his walk. And then at some point, he comes over the ridge. He sees the bull. And this was a very scary experience, because when he saw that bull, the bull was already getting up on its haunches. And this scared the living daylights out of him. And he turned around and ran as fast as he could out of that field. The interesting thing is that when he finally got out of that field, which he did, he discovered that he was in terrible pain. He had torn ligaments, more than one ligament. He was in a hospital for more than a month after this because of the damage he had done to his leg. But the fear got him going, and only when he was finally safe did he notice the pain. And what's happening here is, in this case, you can see, so I'm trying to just point out, you have this fear going up, but then at some point it's taken over by the pain. Okay, well, so there, you've seen that. This is pretty much the entire conscious Turing machine. A few things. Let me just point out a few things about it. There's no signals from the input to that short-term memory, the stage. Nothing going there. Nothing from the short-term memory to the external output. Everything is going from the inputs down to the bottom. Your eyes, what you see, is going to the appropriate processors. Your ears, what you hear, going to appropriate processors. You see these arrows coming from different locations, going to appropriate processors. Those processors can then lead to these outputs. Could be a hand, could be a leg, etc. What's on the stage is sort of out of it. So, you know, it's interesting. You touch, have you had this experience? You touch a hot stove and your hand pulls back. And in fact, the signals from that hot stove just go up to your spinal cord and then go right back. And pull your hand back. And you don't even know that, you're not consciously aware of it till afterwards. It's fun, it's really fun. And you know, we thought that we were consciously pulling back, but it ain't the case. You are consciously aware of it afterwards, and you realize, that's not a good thing to do. And the amount of time between the time the processor has made its move and you are aware of it, you feel like you made the move, but the amount of time between the time when the decision is made and you are actually consciously aware of it can be up to 10 seconds. You know, it used to be 100 milliseconds, 300 milliseconds. There are examples where it's up to 10 seconds. A few other things here. You'll notice that there are these links. I think of every neuron in our brain as being the root of a processor. Each neuron, view it as a processor. There are 10 to the 11th neurons. You cannot possibly have them all connected. So it's 10 to the 11th times 10 to the 11th, 10 to the 22nd, you know, 6 times 10 to the 23rd. It's Avogadro's number. It's a lot. You cannot have all those links. Just no way. And in the model, what happens is a link is created when a processor asks for information from the stage, asks, what's her name? And then it gets answered by another processor, and that begins to grow a link from the processor that answered to the processor that asked the question. And this is the way in which stuff that you do consciously gradually becomes unconscious, coming down. Okay, and what is actually being sent up through these nodes in this model is, first of all, the information is what you know of. It's that information that's being sent up there. That's a certain amount of information. You remember that house that's upside down? It seems to us like we have a lot of information there, right? You have this whole house. But actually, you don't have much more than a sentence or two. The vision people call it the scene gist. You have just the gist. And it's enough, and when you dream, to be able to create that wonderful memory. So it's the information that you're aware of. The weight, you're somewhat aware of. The address, not at all, because you have no idea where this information came from. But for other purposes in the model, you have that. That's what goes up there. The address, the information, the weight. And, okay. So conscious Turing machine. So how processors choose weight. I told you already about a pain processor. You scrape a knee, how the weight is chosen by how many nerves are firing and how fast they're firing. There's a context processor, that's more often on the stage. It just gives you some sense of the context. But you know, when you need to do something like figure out that next move in chess, you can put the context out of your mind altogether. You need everything you've got in that short-term memory. You can do that. And then there's this business about weights, that a task that has been put off has weight that grows as a function of its importance and the time remaining to complete it. So you know you have a test in a week, it's okay. Then the next day it begins to bother you, and then the next day bothers you more, and so it goes. Details of the dynamics. There's a threshold for allowing processes into short-term memory, and if it's set too low and too much gets up there, then the way things work, a lot of the complication was the fact that in this model, very little gets up on the stage. There's actually only just one node at the top of this model. And the way you get other ideas coming up is that when a process is up there, once the process is up there, its weight starts to go down. And something else that it was trying to get up there can now take its place. And when it takes its place, its weight starts to go down. When it gets off the stage, its weight starts to go up. There's small amounts. And so there's something very interesting that comes out of this. You can have this bubbling of ideas. If the threshold is set too low, you're getting too much of this. Lots of ideas bubbling up. And that's our explanation for mania. You know about manic depressives. The manic is getting lots of ideas, none of them really thought about very carefully, making them manic. If the threshold is set too high, it's the absence of ideas that produces depression. Threshold set too high, there's just nothing coming up there. It's a very unhappy world when you don't have ideas. So anyway, so this is about losing weight when you get up there. Oh yeah, this is about links. I told you about this already, that when processor A gets a link from B, when A calls B and B answers, that's what this is about. Linking, yeah, I mentioned this. Linking enables conscious processing to become unconscious. There's long-term memory processor. I won't go into it. Details of the dynamics. Avram's paper is called the sleeping experts problem, which has to do with managing the fact that the weights may not be quite right. And it's sleeping experts theorem is very nice. It appears in this Foundations of Data Science, which used to be Hopcroft and Canaan, but they have invited Avram to join, so now it's going to be a triple. That's nice. I'm very happy that Avram and Lenore are working. I don't have a paper with them. I would like to have a threesome. Finally, my chance. Recall that consciousness in the model is the content of short-term memory. How reasonable is this definition? So let me tell you the argument I give for why it's reasonable for this consciousness. Remember that what's on the stage is broadcast to every single processor in long-term memory. Every processor knows about it. The reason that you are conscious is that all those processors know. And the one that is in control of speech, it knows about what's on the stage. You know that it's interesting, there are people who have had their corpus callosum cut, so they're like two consciousnesses inside one brain. Corpus callosum cut, you have two brains. One of them has speech, the other one does not. The one that has the speech it does very well, even though it doesn't know about what the other one is doing. And these people with a cut corpus callosum, they say, well, do they go to the market to get some stuff? They reach up and the right hand, controlled by the left part of the brain, gets a can of beans, puts it in the cart. The left hand takes that can of beans, puts it back up on the shelf. This is the way they communicate. How reasonable is this definition? It's the fact that all the processors are focused on what's on stage. that makes it conscious, and what's on stage is closely linked to speech. That's what you are aware of. Here are some questions that come up. Whether my answers are right, I think I have reasonable answers for these questions, but you may disagree. Why is short-term memory so tiny? 7 plus or minus 2. And when we build our machines, we might think that we really should have a lot more up in memory, and it's not clear. It's not clear because you want all those processors paying attention to the same thing. And if you have a lot on that stage, you could have some processors paying attention to some stuff, other processors paying attention to other stuff. Might not work very well. So that's my argument, at least, for why short-term memory is so tiny. And then, what's a chunk? So remember I said 7 plus or minus 2. Those are chunks. When George Miller defined chunk, his paper was called The Magic Number 7 plus or minus 2. He said there are 7 plus or minus 2 chunks. What's a chunk? He never defines it. He says, well, a chunk can be a digit, it can be a letter, it can be a word. It can even be the alphabet. A, B, C, D, E, F, G. It could be that. What the model is suggesting is that the chunk is a pointer. It's a pointer to that letter or digit or word, or the root of that singly linked list, which is A, B, C, D, E, F, G. Kind of fun. Isn't it interesting that the brain somehow has its own way of deciding what data structure to use? We all know about data structures, but actually, how come the brain decides to store the alphabet in a singly linked list? There have been plenty of times when I wanted it to be doubly linked. In fact, I even at one point decided I would learn the alphabet backwards because I wanted doubly linked. If you make up a ditty, you can do it. G, Y, X, W, V, U, T, S, R, Q, P, O, N, M, L, K, J, I, H, G, F, E, D, C, B, A. So you can do it. You make up a ditty. Thank you. You make up a ditty, and what I discovered from this is that I now had 2 singly linked lists in my brain. I still can't, if you ask me what comes before P, I have no real way to tell except working forwards. Okay, here's chunk. Why am I interested in consciousness? Yeah, why be interested in consciousness at all? Well, it's obviously useful to humans. I mean, you know, we have it. It's useful to us. If you don't have it, then they talk of being a zombie. That's like, remember in that model, the short-term memory basically is watching what's going on and getting information from below. But the input and the output, no connections directly to it. If you leave out that short-term memory, you're a zombie. What consciousness? It focuses those processors on creating the current best interpretation of the world. I think that this is very important, that consciousness is a way of making sure that you've got the right model of the world. You've got all these processors looking at it, they maybe have different ideas of what's going on there, and it focuses these processors on creating the current best interpretation of the world. And so it's a checker on that interpretation. You are constantly checking yourself. And this gives the entity the ability to solve unanticipated problems, to deal with a complex world using all the tools at its disposal. And finally, there's this fact that when I was a kid, I really wish I had a manual for the brain. I mean, here I was, I wanted to know how to think, and no manual. Very upsetting, actually. So I wanted a manual. So for me, my interest in this is because I really still want to get that manual for the brain. Okay, so I've talked about this. We're getting close to the end here. You'll be glad to know. This is a story about Oliver Sacks. This is a story about recollections and dreams. I'll just tell you an interesting story, and I won't get into it very much. But you know, if you saw that upside down house, so how it looks like, you know, if you try to imagine it in your head, it's not quite the same thing. You can close your eyes. You don't see it clearly the way you actually see it in real life. And if you have a dream about it, it's much clearer. Your lucid dreams are great for this, because if you have lucid dreams, you will see that house the way it really looks in real life. If you've had lucid dreams, you know that you can, if you realize you're having it, you can bash a window and see the shards of glass falling too slowly. One way of telling that really you are in a lucid dream. So look at this difference. How come would you, as an architect, hey Carlo, wouldn't it be wonderful if when you close your eyes and imagine something, if you saw something as clearly and real as you do in real life, or as clearly and real as you do in a dream? And the information is there because it produces a dream. How come you don't? And I have an idea why you don't. Yes. So for a while, I really tried to remember my dreams. I really spent a lot of time. I got into lucid dreaming. I could remember my dreams. And then at some point, I discovered that I couldn't tell if what I saw was real or if I saw it in a dream. Confused. And at that point, I realized this is a bad idea. I stopped trying to remember my dreams. So I think there's a reason that we don't remember our dreams. I think it's a bad idea. And I think also when you try to close your eyes and imagine it, it's probably a good thing that you don't see it as you do in real life, so you can distinguish the two. In fact, one argument for this is that you know that schizophrenics often hear and see things that aren't there. And this is a case where they are, in fact, seeing things that are not there. And they can't distinguish what's really there from what's not really there. And then you have schizophrenia. That ain't good. So, lots of examples. This has to do with theorems. Oh, I never got to the hard problem. Okay. Yeah, so why? Why interested in the hard problem? Why should one be interested in the hard problem? In the hard problem for pain? Why should we want machines to actually feel pain? So, you know, machines are expensive. You want them to take care of themselves. So you'd like them to be able to feel pain so that they can take care of themselves. And if you understand how pain is formed, you could even make it so it feels your pain. And make it feel your pain. How might the conscious Turing machine experience pain? We're almost done. How might the conscious Turing machine experience pain? So let me just say that we tried many explanations for this. And here are suggestions that don't work. As attested to, for example, by these asymbolics. Pain might arise from observing unconscious reactions such as grimacing, crying out, and such. But these asymbolics tied to, they cry, they grimace, but it's okay. They're not bothered. It cannot be their observation of this that's causing that. A response to painful situations, such as a finger pulling away from a flame. That's not what's causing the pain, because you sweat and increased heart rate, muscles that vibrate involuntarily. There are many possible things that we consider that cannot be explanations for pain. Here are our suggestions for extreme pain. They're just two. The first is the most important. And that is that has to do with the broadcast, that extreme pain is an actor that takes over all short-term memory. It takes over. It allows nothing else up on the stage. Pain messages and only pain messages are broadcast. Every processor knows of the pain, and no other processor can get up there. If you recall the story of Oliver Sacks, The fear was the first thing that got up there. It had the highest weight. It got up there, and it did not allow anything else up on the stage. It did not, so he did not feel the pain until he got out of the field. The fear weight went down, and now the pain went up there, and he felt the pain. So it's the fact that, so I'm talking here about extreme pain. Lesser pain means you may allow something up, but not that much. And the confirmation of this, here's an interesting thing. So, you know, we would like to actually have ways of disproving all of this. Here's some confirmation. Under conditions that produce great pain, asymbolics can think while normals cannot. Under the greatest pain, you cannot play chess. Might want to, you cannot. An asymbolic can, under the greatest pain. The asymbolic can play a wonderful game of chess while holding a frozen can of Coke in their hand, and I cannot. This is an argument for the difference that, for us, the pain, when it's up there, allows nothing else up on the stage. And here's a very funny argument. Isn't it sort of strange that in a Darwinian design, you might expect that when you feel strong pain, that you should be able to think? It's the time when you need to get out of that. You know, you're caught in a trap, you need to be able to think, and yet the theory is saying, you cannot. You absolutely cannot. So, okay, well, it's very anti-Darwinian. Oh well. But does this account for the sudden excruciating pain at the moment? You tear a ligament, and the answer there is that there's just something different from broadcasts, which is interrupts, that the moment you have this great pain, all of the processors are interrupted. They must put whatever they're thinking on a stack, and they must pay immediate attention to that pain, and that's behind what's causing that sensation of extreme pain. And this is an explanation of it, and this is another hard problem, which Lenore is going to be giving this talk in Beijing. She's interested in joy, and so she'll talk about this, and she has ideas of what's causing that. There's a whole part of this talk on free will. I think this model gives you a very wonderful idea of what free will is about. And I'm going to keep on going and get to the end.
So if the key element for consciousness is short-term memory, it seems rather simple to put consciousness into robots, because we know how to construct short-term memory. What are we missing then? What is still not quite making consciousness? We just have short-term memory.
You think there's something more than that? It's a short-term memory, but also that short-term memory is broadcasting to every single processor that's there. It's not just having short-term memory, but having it broadcast. If any one of those long-term memory processors is responsible for consciousness, it will be aware of what's going on.
Okay. So you also mentioned that Bernard Bars, in a way, has a way of measuring and quantifying the amount of consciousness. Can you tell us what is the essence of that?
Very good. One of the people that I mentioned is Tononi, and he has an information theoretic measure. Tononi is great. He's a doctor, he's a surgeon, he knows information theory. How many surgeons do you know that would know information theory? And he has a measure of consciousness, and according to that measure, a thermostat has a tiny bit of consciousness.
What are the elements that he puts in that equation?
Mostly that this business going up and down. You see here, information is broadcast, and then something comes back up, and then it's broadcast.
So the bandwidth of communication between short-term and long-term memory is the key element?
Yes, it's the key element.
On that, I have one more point. I have a little problem that you have signs in front of the fear and pain and so on. So you have a clearly binary world. There are good things and there are bad things. Well, and I think that's very dangerous, because there are probably elements that you cannot classify.
Yes,
and so
each processor, you know, I said each processor chooses its own weight, decides on its weight. The pain processor decides on its weight, it's negative. The joy processors decide on their weight and it's positive, but you know, maybe it's, you're curious about something. Is that positive or is that negative? The processor that sets the weight is also deciding whether it's a positive or negative weight. And that can change. The same processor can sometimes decide this is positive, thinks it's good, sometimes that it's negative.
Hi. So I was interested, you started off talking about a homunculus and the recursive problems with that, but why is the short-term memory processor not a homunculus?
I didn't say it's not. That's the closest thing to the homunculus, right?
So, but then aren't we still stuck with the recursive problems of trying to understand a homunculus?
Well, it's, how do I answer that?
You got a model, you got a two-level model, right? I don't think there has to be something more level to the model.
I don't know how to answer your question. I'd have to think about it. Over here. Hey, just speak it out loudly. What's your question?
So I'm wondering if the specializations of the processors is predetermined, like pain and joy, for example, and can you explain, for example, the sleep disorder you mentioned, or face blindness, or sociopathy, or whether or not some of these processors exist or are working?
For sure. Yeah, so the question is, do the processors, are their functions decided in advance, or is it decided after the fact? And pointed out that there is a part of the brain called the fusiform face area that's specifically interested in faces, really interested in faces and the names of faces. And if it's shot, then the person whose fusiform face area is gone doesn't recognize their wife, their kid, doesn't even recognize themselves in the mirror. Can you imagine looking in the mirror and not recognizing who that is? It's a terrible thing. You don't want to have that be shot. What? Okay, so that doesn't answer your question. I think that many of these things are built in. There's a part of the brain called the amygdala. And if you have a certain genetic disorder, the amygdala will be calcified, and if the amygdala is gone, you will not feel fear. It'll be like fear asymbolic. You simply won't be afraid. And just like with pain asymbolic, people with that condition rarely live very long. You know, they're not afraid of a car coming or whatever. So,
hi, Manuel.
Specialized amygdala.
Hi. You explained about this model of consciousness, but I cannot understand what is the process in your model that creates experience? Where exactly is the...
Well, I gave you a hint of it. I gave you a hint of it when I said about these connections between long-term memory processors. That if a processor A asks a question, wants some information, it goes, basically that request goes up to the stage, it's broadcast, and then maybe B, processor B, answers it. And if B answers A's question, then that begins the process of creating a link from B to A. And after a while, if enough such links are created, A's question doesn't have to go up to the stage. And whatever they're doing becomes unconscious.
Yeah, but the experience itself, right? So in consciousness, we have an inner experience of the world. We are not zombies, as you said. And I didn't understand, so what is this experience? How in your model, what is the process that makes it that now we have a conscious experience? Why it's not, we are not zombies like any other computer that makes algorithms, your algorithms, why they create an experience?
Yeah, so we can start with the talk all over again. You know, experience is partly the lateral connections. Experience is coming in and knowing how to weight. Remember I said that Abram's algorithm tells you how to set those weights? how to modify those weights, experiences coming in that way. But you know, this talk was terrible because I told you nothing about how those long-term memory processors work. Although I did say at the beginning that all the heavy lifting is being done by them. So here, it's being done by those long-term memory processors, and I haven't told you how they work.
Yeah. So yeah, you know,
This is such a fascinating topic. People have many questions. So we need to get over this. Over here.
Talk to you later about that.
Hi, Manuel. Hi, it's George.
Oh, George Lakoff.
Hi,
It's
good
the
to see you,
George.
man.
How nice. Thank you for coming.
What about the experience of consciously putting things out of consciousness? You're writing a chapter of a book, a thought comes in, you have to pay a bill, you go back to writing the chapter of the book, right? You're
Yes.
consciously putting things out of consciousness. Does that work in your model?
I kind of talked about, you know, Poincaré having gone on vacation, had clarified the problem and put it out of the model,
Okay.
put it out of consciousness, and yet the processor that was working on it bubbled up the answer when it got it, when he wasn't thinking about it.
But this is really putting it out of consciousness until you're done. That is consciously keeping it out of consciousness until you're finishing that chapter of the book.
Okay.
How
He
does
was
that
keeping
work?
it out of consciousness until
But-
he got a solution. He didn't even know he'd get the solution.
So how does that work in the model?
There are processors working on whatever problem you give them. There are many processors working on it, and probably trying many different things. And when a processor finally finds something that it believes to be right, it gives it a high weight and it begins to work its way up to consciousness.
Okay, cool. Thanks.
So it seems like the short-term memory plays a really crucial role in your model. So you mentioned at the very beginning, people can tell between living and not living, alive or not alive. If you got rid of, in your model, if you get rid of the short-term memory and its capability, or just even getting rid of the capability of actual broadcasting, how would you classify the remaining portion? Will you still call it sort of a living being in this sort of philosophical discussion?
Well, first, thank you for the question. Secondly, I don't understand it. It's probably a very good question. Well, can somebody translate for me? I just have a trouble. I'm partially deaf, and you're too far away for me to be able to read your lips. And so somebody explain.
Should I just be louder?
No,
Oh.
that doesn't help. But you may say it again, and maybe Faith next to you will listen and tell me. Say it again.
So I'm just saying, like, if you get rid of the short-term memory, would you still consider as a remaining conscious Turing machine?
Then you have a zombie.
Okay.
You don't, because what's making you conscious of stuff is that what's there is being broadcast everywhere. Otherwise, the input is going to different processors, the output, and those processors are not talking to each other. There are a few links, but not many.
But you did argue that those processors communicate with each other to calibrate the weights, and I figure that is actually
I didn't tell you where the calibration was coming in.
Oh.
The processors communicate because this processor answers that processor's question. So that starts the communication going.
But there must be
basically, there's just too much. Yeah.
Okay.
No, they want to actually get out. So.
Okay. Manuel, so what do you think is the development over development? So children, when they are born, a baby, when he or she is born, from the moment of birth through growing up, there are phenomena like people don't have memories of what happened to them when they were 1 or 2 and so forth. So can you tie that to how it would be in your model? How do you connect that to your model?
How you connect those memories that they have?
How does it evolve as a child grows up from birth?
Those memories that the child has that it's already forgotten about?
Yeah.
Is that the question?
No, I don't think that was my precise question. My question was, how do these two stages change over the growth of a baby?
There's some neuroscientists that believe that everything you ever saw, heard, is stored in your brain. It's all there. It's all there. You not necessarily available to you, not necessarily available to you, but that it's there. And so there's this interesting case where, you know, brain surgeons go in, they want to find out where the epileptic fit is coming from, and they stimulate a neuron, and then the patient who's awake and here says, "Oh, I'm in bed. The door's opening. My mother's coming in. She's carrying a tray. She's bringing it to my side." It's exact. And then, "Oh, I'm in bed. The door's opening. My mother's coming in. She's bringing a tray to the side." This is a memory that the person absolutely has no recollection of having, but it's there from early.
So it's all there in the long-term part.
All there somewhere, yeah.
Okay, you have a mentor-student relationship. There you go.
So you had the the study of pain, the study of joy. You didn't tell us much about joy, but and then you mentioned mania and depression. So it's kind of well known, or at least I know it. I don't know if it's well known, but people who are kind of bipolar, right? They're very creative. So it's often an association.
Ideas bubble up.
So it's an often association that people who are bipolar also are creative, at least during the manic phase. So how does that consist? Is that something that can be
tapped?
No, does your theory explain that?
It just says that in the model, there's some, you need to have a threshold for other reasons.
Yeah.
And if that threshold is set too high, no ideas come in. And if that threshold is set too low, then ideas bubble up into, they're simply not thought about long enough to be really good ideas, but they bubble, and you're happy because you're getting lots of ideas.
So you're saying that creativity is ideas that actually don't make sense, but they are.
Some of them make sense.
Okay, well.
All right, let's take for a fast.